Hello everyone. Tonight or in this video we're gonna make your life a lot easier regarding the line integrals. We tried to prove that the line integral can be connected or can be changed to a double integrals, means avoid parameterization, avoid using differential. As long as you give me a path and give me a vector field, I can evaluate the line integral. The method was proved by Mr. George Green. That's why we call it Greens Theorem. And he only lived 48 years. What a great life. British mathematician. And he said, if you do have a very simple connected region, such as this, I said simple, it could be a circle, it could be an ellipse, it could be crooked, but the condition is that the starting point and end point must meet, and it must be counterclockwise. These are the conditions. Simple region. What I mean simple region? You cannot have a region and you have another region inside of it. That's not a simple region. Whatever the curve is must be the boundary for the whole region. I mean, that piece of property must be bounded by that curve. You cannot split a property in three different places, an island, and water here. No, you cannot. And also, they cannot be disjoint either. And they also cannot be overlapped. It has to be very simple, like a circle, counterclockwise, like an ellipse, counterclockwise. It could become part parabola, part line. It could be any combination, but it has to be a simple region. That is the condition. If we do have that condition, we can write a vector field in terms of a double integral. You're gonna have some integrand in here times dA, and that dA is the area of that region. And what is the lower limit and upper limit for these two is right here. Therefore, I need the area of a region times that integrand we try to prove. Let's review the line integral. The line integral said if you have a vector field, you have to dot it with a unit tangent vector times the arc length. Because when you do have a path, and that's the path, and if you have a vector field, that vector field has x component and y component. In order for moving around the path, which you're trying to find the curve, or you want to try to find the circulation, you need to take that f and project it over that one, which is f dotted with a projection over the magnitude of the t squared times the t. But I only need a scalar quantity, and the unit tangent vector, the magnitude is 1, therefore you have f times t. But remember, what was ds and what was t? T was r prime of t over the magnitude of r prime of t, and ds was the magnitude of the r prime dt. Here how we write your line integral into a parametric parameterize the vector field and the arc length, and we can write it that way. But please pay attention, that vector field, if it's an R2, there is function of x and y here. There is a function of x and y here. Sometimes I call f of x, y, m and g of x, y, n. That is a vector field, but you gotta dot it with r prime. And r prime is nothing except dx dt, dy dt, and that become a dt. And this one is t, and that's become, I have not parameterized this, and that become the line integral. Therefore, your line integral, if I multiply the dt by these vectors, that become m dx, because you have the dot product, plus n dy. Remember, this is the x component of the vector field, and this is the y component of the vector field, and instead of f of x, y, I call it m and d. Okay, right now we're gonna start Greens theorem. I'm gonna take a region, and I'm gonna say that region is counterclockwise, and that region is not a graph of a function. Therefore, what I do right here, I'm gonna go find the a here and a b here, and I'm gonna cut that region in half. The bottom one passes a vertical line test, the top one passes a vertical line test, and in order to find the area, I'm gonna make my x fixed. I'm gonna do it respect to x. Therefore, this is, I can call this one the bottom function, f of 1x, and this is become the top function, f of 2x. Okay, right now, I want to write that part of your differential. There are two parts, this one and that one. This is, I'm going to make my x fixed. Here I'm going to make my y fixed. Somebody said, how you going to make your y fixed? I make my region like that. I'm going to call this one a C, call this one a D, call this one G, that's a right one. Remember, bottom and the top. Therefore, in here, that it depends how you're gonna do that one. Therefore, I'm gonna say the right one, but that's G of Y, because I'm making my Y fixed, but my X changes. G of 2 right and G of 1 left. I'm gonna do the same thing for here while I'm gonna do this one for that one. Therefore, for that one, I have to write two different differential. I call this one C1, I call this one C2. I say C1 is, okay, I'm starting from C1. From A, I'm writing the C1. From A to B, M dx, I'm gonna do this, A to B, plus B to A, M dx. I'm gonna do the line integrals, and I'm gonna say this is for C1 and this is for C2, and the whole thing become the C. the path. Okay, what did I say that m is? That m is a function of x and y. The n is a function of x and y. Therefore, what I'm going to do right here, I'm going to write a to b, and I'm going to write m, but m is a function of x and y. But what is your y? F of 1 x dx plus b to a. For that one, my m is a function of x and y, but x is x, but your y is f of 2x dx. I can write this one, see, that's a to b, that's b to a. They have different lower limit. I can switch this one and bring the a here and move the b here and change the sign to a negative. Then I have same lower limit, same upper limit, and I write it as a sum or a difference of one integral. A to b m x f1 of x minus m x f2 of x, all multiplied by dx. That was half of the line integrals. That was this half. Okay, I did evaluate the line integrals, and if you tell me what the m is, I can easily go from a to b and using differential, tell me what is x, what is the path, find the x, find the dx, and evaluate it. But I'm going to come back right here, and I'm going to say, what happens if I take a double integral of that region? See, I'm going to do double integral of that region, dA. But I do the same thing. But I'm going to take the partial derivative of m respect to y. Just don't ask me why, just watch. I'm going to do it with respect to y. Since my x is fixed and my y varies, I put my x from a to b, but my y is going to go f of 1x to f of 2x, and that becomes partial of m, partial y, and but here because y varies and x is fixed, I put the x at the end. Well, in order to integrate, I need the differential. But remember, this is partial m, partial y, dy, they gone. All I have is a partial m. And derivative and integral, they undo each other. Therefore, if I cancel these two, I have a to b m. Please remember that m was function of x and y from f of 1x to f of 2x. Don't forget, I have a dx in here. Then this is equal to a to b m. X is have not been integrated yet, x stay constant, but my y become f of 2 minus m x constant and f of 1, and I have a dx. If you look at these and you look at these, they are not the same. Therefore, this one and 100% this one are not the same, but they are very close. How can I make them look alike? If I factor a negative here, I have a to b, negative become a positive, x f of 1x minus m x f of 2x dx. Right now, this one, which is the double integral, and taking the derivative of the x component of the vector field respect to y. That's what it is. Taking the partial derivative of m respect to y. Okay, remember that if you do have a vector field, you can take the x component and differentiate it with respect to y. Okay, that's what it is. And these are exactly the same. Then from today you have to know m dx c is the double integral of r partial derivative of m respect to y dA. We proved this portion, only that portion, and that one was half of your line integrals, and your line integral written in differential form. After we parameterize it, we cancel magnitude, and this becomes dx dt. The dt cancel with that one, and it only become differential. Now I'm going to go to that region, and I'm going to say I do have partial derivative, the line integral of n dy, because remember, the line integral of f dot dt ds is the same as m dx plus n dy. Some book call this one f of xy dx, and they call this one g of xy. It depends what textbook you are in. That's the notation they use. Okay, the region is here. This is a counterclockwise. I started from C, and I call this one the right. Why? Because when my y get fixed, my x changes, and x is a fancy way of writing x is f of y. Go to D, come back to C, and this is the left. Then I'm gonna write for the C, C1 plus C2. This is my C1, this is your C2. I'm gonna write the curve integrals or the line integrals of n. Remember, n is a function of x and y. dy, that's your C1 plus C2 n x and y dy. Your C1 go from C to D. If you go from C to D, you have n. In here, remember, n is a function of x and y, but in here your y is fixed and your x changes. Therefore, in here I'm going to write G2. That's for the C to D. That's for the C1. That's for the C1. Instead of x and y, x is G2y, but y is fixed. Plus D to C, n, function of x and y, x is G1y, but the y is fixed, and both of them have dy, which I forgot on down. But the lower limit are not the same. I switch the lower limit and I'll make a negative. Therefore, from today you have to know n dy is C to D n G2y comma y minus, help me, n G1y comma y all dy. Okay, I find part of the line, the differential form for the line integral. Right now, I'm going to change to a region, make my y fixed, but my x, you have the left and you have the right. Your x is varies, your y is fixed, but I'm gonna do the partial derivative. What did I do over there? I did partial of m. I hope you remember partial of m, which it was the x component of the vector field. I did it respect to y. I'm gonna do the y component of it respect to x, and these two gone. And integration and differential, the rules undo each other, and that's become only n from c to d. Your n is a function of x and a y, but it go from g1y to g2y dx. Then this become c to d. N, remember x is varies. X is g2y comma y minus, because you have to put f of b minus f of a, n g1y comma y dy, which is dy here. Tell me, is this and this exactly the same? Then from today you have to know, in previous one, when we had the partial of m respect to y, dA was exactly equal to m dx, and the partial of the region of dA, a partial of n respect to x, was the line integral of n dy. And remember, I made a mistake right here. That was a negative. It was not a positive. That is a negative right here. And I hope I did write it correctly, and I didn't write it correctly, because this one here is a negative. Therefore, this is not equal to that, because this one is, please pay attention, this one m dx is this, and this one is this. But when I factor a negative, they become the same. Then partial of m dx is negative partial of m dy, partial of y dA. I corrected my mistake here because I had to factor a negative. Therefore, this was this, and this is this. But what was the line integral in differential form? It was m dx plus n dy. I can write this one as mx, I can write this one, and n I write this one. But both of them have dA and the same region as a common factor. I write it as a double integral of a region and a dA. But I write the positive first, because remember, this one can be commuted. This can become n dy plus m dx, additional commutative. Therefore, I write the n first, which is partial of n respect to x minus partial of m respect to y. This is called Greens Theorem. It takes the line integral and tie it to area of a region, as long as the region bounded by a simple curve and it is counterclockwise. Then somebody said, I need help, Ganji. I have a vector field. That vector field is x squared y, and 2yx. I just made it up. But my path is this path. Y equal to x squared and y equal to x. They do have a point of intersection at 1 and 1 and 0, 0. I want you to do me a favor. This is a path, and I want you to find the work done by this vector field that moved an object from here to here and bring it back in here. Or do the circulation. I don't know. Let's do it. First, this is m dx plus n dy. I write this one as a Greens theorem of a region. But remember, the partial derivative of n respect to y was a positive, and the m respect to, n was respect to x, because y, this is nothing except f of yx minus f of xy. If you want to really know it, it's just a chain, the second order, right there. And I hope you know if these become equal to each other, that's called conservative. And if these are equal to each other, that becomes 0. Therefore, if the conservative, well, how much work you have to do from here to here? 0. Therefore, if this becomes 0, you know that's a conservative force. And this is a partial derivative of y dA. Okay, let's find the area. X, I'm going to make it fixed. Y, that's the bottom. That's the top. dy dx. That's the area. But what is your y component of the vector field? 2yx. Do it respect to x. 2y. Minus. What is the m? X squared y. Do it respect to y. X squared. Well, do this one respect to y first. 2y squared over 2 plus x squared x squared y, because you have to do respect to y, that's x squared y, from x squared to x. Therefore, you have 2x squared over 2 plus x cubed minus x squared become x to the power of 4, x squared plus x to the power of 4. Therefore, this is x squared plus x cubed minus 2x to the power of 4. Do it respect to x from 0 to 1. That's x cubed over 3 plus x to the power of 4 over 4 minus 2x to the power of 5 over 5 from 0 to 1. And that becomes 1/3, 1/4, and negative 2/5. Do you want to go parameterize it? Go do it. Do you want to do the line integrable differential? Go do it. I do the Greens theorem because the region is so nice, neat, and clean. But please pay attention. I want to show you something. Somebody said, why this region said partial derivative of the y component respect to x and the x component respect to y. You want me to tell you why? You know why this is negative, why this is positive? Well, I have a vector field. But please remember, as the x increases, the y component, look at that one, the y component, as the x increases, the y component of the vector field, the y component, as the x increases, the y component, the y value get larger and larger. Because this is nothing, the y component. And y component is your n. Then n is going up as x increases. And this is nothing except circulation. That I want to know how much circulation does it do right here. Therefore, I know the y increases as the x increases. Therefore, this is positive. But I want you to look at this one right here. And I want you to look at right here. And let me what happened to the x component. See, I go here and here. 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 What do you do with my x component? My x component decreases for that one. Respect to what? Respect to the y. Therefore, when y changes, my x decreases. This one is saying my x component respect to the y decreases. Do you see why this is negative? Do you see why this is positive? And that causes the circulation. That's another proof for it. Therefore, today you have to know that the Greens theorem is tied to a line integral, and we used differential form to prove that yes, by Mr. Greens theorem, that the line integral is equal to a double integral you tie to area of a region only and only if it's a simple region. But sometimes somebody said, what happened if the whole thing become one? If the whole thing become one, that become area of a region. Therefore, the line integral is nothing except area of a region. Somebody said, what happened if they become equal to each other? I said, excuse me? If they become equal to each other, I said, okay. The only reason they can become equal to each other means f of xy become equal to f of yx if your vector field be a gradient. Not all the vector field are gradient. Which one are gradient? The one you have a potential function. If it's a potential function, then the gradient could become a vector field. But if the vector field if the vector field cannot be tied to a potential function, that's not a gradient. If it can be tied to a potential, that's called conservative. And what is the curl of the conservatism? Curl, you have to take it, the operator, cross it with the vector field. Therefore, I do partial x, partial y, partial z. But this is your m, x component, n, y component, and p is a z component. Okay. If this is your gradient, means the vector field is a gradient of some multivariable function. Therefore, this is already partial derivative respect to x. This is already partial derivative respect to y. When you do curl, when you're doing the I component, you taking the partial derivative of z respect to y. Therefore, that's the partial derivative of z respect to y. That's called f of, help me please, partial derivative of z, we already taken it, doing it respect to y. But the other way around, that's the partial derivative respect to y. That's the partial of y, you're doing it respect to z. But for the j component, you're doing the z respect to x. And you're doing x respect to z. And for the k component, you're doing partial of y respect to x and partial of x respect to y. Oh, What was my Greens theorem? What was my Greens theorem? Oh, that's the Greens theorem. Then, if this is conservative, f of yx should become equal to f of xy. And if these become equal to each other, that's become a 0. If it's conservative, that becomes 0. If it's conservative, that becomes 0. Therefore, conservative, the curl of the vector is 0, means there is no rotation whatsoever. Then, from today, you have to know, if this becomes 0, it is a conservative force. And it has no circulation. And they call it irrotational. I hope you enjoyed the video. Thank you.